Welcome, this is Dr. Plague, and in this video I'll start designing and building a clock source for future homemade CPUs, or whatever we want to use it for. Now, if you saw my videos on the Plague Mark I homemade CPU, then you saw me using the benchtop waveform generator to produce the clock signal. I don't want to rely solely on this waveform generator. When I get to more complex CPU designs, I'll want to be able to start and stop the clock signal. I want a way that I can manually clock the CPU. For instance, let's take a quick look at DigitalWorks. They have a button up here where you can step the clock, and by default it steps in half clock cycles. You can also choose full clock cycles, but I like the half clock cycle option. Parts of the homemade CPU may respond to a positive clock edge, and other parts may respond to a negative clock edge. So, what I'm looking for is a momentary switch that will toggle the clock from low to high on one press and high to low on the next press. Then, repeat. I could also make it such that pressing the switch will provide a high signal, and releasing the switch will give us a low signal. But I do like the idea of toggling the output between high and low. That way, if I want to probe the circuit when the clock is high, then I don't have to keep the switch pressed. I also want the ability to start and stop a running clock, which could come from a waveform generator, a crystal oscillator, a 555 timer, or whatever. I'm looking for something similar to the Altier 8800. If you're not familiar with the Altier 8800, it's a home computer from back in the early 1970s that featured the Intel 8080 processor. It was built in a fairly good-sized box-style enclosure and has a front panel that consists of a bunch of blinking lights and switches that you could use to program it and execute instructions, like this. What I'm interested in are these two switches right here, the run-stop switch and the single-step switch. What I want is a run-stop switch that will start or stop the clock source that is feeding into it. I also want a single-step switch that will manually toggle the clock signal when it's in the stop mode. I know that this is not identical to how the Altier uses these switches, but that's how I want mine to function. Now, to get started, we need to make sure that whatever type of switch we're using does not have any bouncing, or else we'll get unwanted clock transitions. Since pretty much every standard mechanical switch can experience switch bounce, I'll need to build a circuit to debounce it. But first, let me demonstrate what I mean by switch bounce. So, this is the type of momentary switch I'm considering using, at least for now on the breadboard. There is something that I've noticed with these switches though. They hardly even need any debouncing, which is great, except for when you're trying to demonstrate a failure. Let me show you how good these switches are. I'll put the switch right here, and pull it up with a 100k ohm resistor to VCC, which will be 5 volts. Then connect the other end of the switch to ground. And, of course, I'll connect the power supply up to the rails. And put the oscilloscope probe right here. This is the schematic for what I have built up on the breadboard. When the switch is open, we should see 5 volts at the oscilloscope probe. And when I close the switch, it'll ground this end of the resistor and we should see 0 volts. Let's give this a try. Look at that. I didn't see any bounce on that switch at all, but that still doesn't mean we don't need debouncing. I'm sure that switch will bounce at some point, maybe not as often as others, but we can't trust it to be perfect at all times. And by the way, in case you're wondering, I did try single triggering off the opposite edge of the press and releases, and the scope caught nothing, so those little tactile switches are near perfect. Since I couldn't get the tactile switch to bounce, let's try out this switch. This one should give us some good bouncing. However, it doesn't quite fit over the center divider on the breadboard. So, I'll just change this up a little. Okay, let's give this one a try. Yeah, we got some bounce there. Ah, that looks nasty. Now, there are many ways to build a switch debounce circuit. The Altier 8800 appears to use 74 123 monostable multivibrators. By the way, the schematics for the Altier 8800 are available on the internet. At least when I looked, they were. You can search for them if interested. There is an app note put out by Texas Instruments on the 123 monostable multivibrators. SLVA720A. It mentions that the 123 makes an ideal choice for switch debouncing applications. However, I tend to disagree. They give a schematic here showing how to debounce a switch. And down here, they give the component values, which are 100k ohm resistors and a 0.1 microfarad capacitor. And notice that they're using the same circuit that I made to connect the switch to the input. Now, while this circuit may debounce a switch press, I am very doubtful that it will properly handle a switch release. Switches can bounce on both the press and release. Since the 123 will produce a single pulse when the switch is closed, it should work fine for switch presses. But if the switch is released after the pulse is finished, I would assume bouncing on the release could re-trigger a new pulse. I want one positive clock edge when the switch is pressed, but I don't want one when it is released. Let's build up a circuit like the one in the app note to demonstrate that it does not work as I would like it to. So let's add in the 74 HCT123. And notice that the pinout is a little different from the 8-pin 123 that is used in the app note, since they're using a single and I have a dual. And I'll connect up the power and ground. I'll add a 100k resistor from VCC to pin 15. And I'll insert a 0.1 microfarad capacitor between pins 14 and 15. Our output will come from pin 13, so I'll move the scope probe to that pin. And I'll connect the switch up to pin 1. And we need to pull pins 2 and 3 to VCC. Then I'll just connect pins 9, 10, and 11 to VCC to terminate the second unused monostable multivibrator in this chip, since I only need to use one for this demonstration. And that should do it. Let's give this a go. You see that? I'm getting a pulse when I release the switch. And there, a bounce got through. Maybe we could improve this a little with a larger capacitor. Let's try a 1 mic. Ah, still flaky. What I prefer doing is to use a low-pass filter on the switch output. And then send it through a Schmitt trigger, like this. Now, if you don't know what a Schmitt trigger is, it's simply an input that has 2 threshold levels. The input needs to rise above the upper threshold before it is detected as a high, and the input will not be detected as a low until it gets below the lower threshold. The capacitor in this low-pass filter slows down the rate of change for the input signal, so it can't abruptly bounce from a high to a low, or whatever. We need to wait for the capacitor to charge or discharge before the level can change significantly. So let's say we press the switch here and release it here. And let's say we get this bouncing. After going through the low-pass filter, we get something like this, where it discharges down to here and goes below the lower threshold, which is then seen as a low. But since the switch bounced here, it charges up a little. But even though it rised up above the lower threshold, it didn't rise above the upper threshold. So it still stays a low, and a similar thing happens when the signal rises. Now, I'm actually going to use a 74 HCT14 as my Schmitt trigger, and this is an inverter, so the output will actually be inverted. We'll get a high when the switch is pressed and a low when it is released. So let's breadboard this up to test it out. I'll just remove this 123 chip and all its connections. And I'll put the low-pass filter in like this. Now the output from the switch will come from between the resistor and the capacitor. Then I'll add in the 74HCT14 and just move the ground wire to pin 7. Now I want to terminate all the unused inputs to power or ground. Then I'll connect the switch to the input of the first inverter, which is pin 1. And the oscilloscope will go to the output on pin 2. Let's give this a whirl. Ah, nice clean presses and releases. This should work very well with the tactile switch that I showed earlier. So that's the debounce circuit that I'll be using in my clock source. But you know what I forgot to show? Let's move the scope probe over to the input of the inverter, which is the output from the low-pass filter, to see just how much better this looks compared to the massive bouncing we saw earlier. Yeah, look at how clean that looks. This is the perfect input for the Schmitt trigger. Well, now let's start looking at how to implement the functionality of the single-step switch. Since we have a fully debounced switch now, we could just use that as the clock source input to the homemade CPUs. That is, if we wanted to implement a full clock cycle with a single press and release. But that's not what I'm looking to do. In any case, let's try out this debounced switch with the last homemade CPU I made, the Plague Mark I with strobing. Let me just disconnect the scope probe here. And here's the Plague Mark I. I'll connect it to the power supply leads. And connect the clock input over to the debounced switch. Now the LEDs should change on the negative clock edge when the switch is released. Let's try it. Looking good. Yeah, that works just fine. Even though that worked fine, that's not what I'm looking for. I want the clock signal to toggle on each press of the switch. For that, we can use a 7474 D-type flip-flop. Let's go to DigitalWorks and I'll show you how I plan on doing this. Here's a 7474 IC. And I'll just connect the clear and preset to VCC. I'll connect up an interactive input switch to the clock input. This will simulate a debounced momentary switch. Now, I could have added a switch and set the type to push to make. Then, pressing the left mouse button will close the switch, while releasing the mouse button will open the switch. But I have found this switch to be a little buggy, because if you click on it and then move the mouse cursor off of it, then it'll no longer open when the mouse button is released. After that, the switch will work in the opposite manner until I move the mouse off of it again mid-press. So I'll just click the interactive input to simulate a switch press, and then click it again to simulate a switch release. I'll connect the flip-flop output up to an LED. This will be our clock source signal. Now, to get this to toggle, I'll just connect the inverted output up to the data input of the flip-flop. Now, hold on, you might be saying. Couldn't this cause metastability, where a signal is basically in between a 0 and a 1? Some people may have a problem with this since there is a setup and hold time required for the data input of a flip-flop. The data must be stable for a specified amount of time after the clock goes high. But how can this be so if we connect the inverted output to the data input? The inverted output will toggle after the data is clocked into the flip-flop, and metastability occurs when the data input changes at the same time it is clocked in. But what we need to understand is that there is a propagation delay before the inverted output toggles. Let's look at the data sheet. The setup time has a minimum of 12 nanoseconds, 18 if you want to go with the extended temperature range. But the hold time is only 3 nanoseconds. We are not going to get a propagation delay that is less than 3 nanoseconds, at least not with the HCT family. Here's a quick scope shot showing the output changing when the clock goes high. And for one transition, we get about 13 nanoseconds, and about 10 nanoseconds for the other transition. This means we should be perfectly safe to use the 74HCT74 to toggle a signal. And, as a matter of fact, if we go down to section 9.1 in the datasheet, we can see that they show how to set up a toggle switch. The inverted output is connected back to the data input, and they're using basically the same circuit to debounce the switch that I implemented, except that I'm using an inverter for the Schmitt trigger. So let's run this in DigitalWorks. And the LED does indeed toggle each time we press the switch. So now let's breadboard this up. Since we know the debounce circuit works, I've switched over to the tactile switch and cleaned it up a little. Otherwise, this is the same circuit we left off with. The debounced switch output still comes from pin 2 of the 74HCT14. Now, I'll just add in a 74HCT74, and I'll put it way over here to leave room for future chips. Then I'll add power and ground. I'm only using one D flip-flop, so I want to terminate the unused inputs to the second D flip-flop on the upper side of the chip, so I'll just connect those to VCC. Then I'll just pull the clear and preset pins high on the first flip-flop to disable those. Then connect the inverted output to the data input. Finally, I'll add the LED. And I'll connect the other end to ground through a 470 ohm resistor. There, we should be ready to test this out. Let's power it up. Each time I press the switch, the LED toggles, which is exactly what I'm looking for. So this is working. However, did you notice that when I first powered it up, the LED was on? The way it's wired up right now, I'm going to get a random result on the LED each time I power it up. Sometimes it may light up right away. Other times it may not. I would prefer the LED to be off each time it's powered up, regardless of the previous state when it was powered down. If we look back at the datasheet, we can see that they show a power on reset circuit. It's basically VCC being sent through a low-pass filter, and then into a Schmitt trigger buffer before being sent to the clear pin on the D flip-flop. We can do the same thing, except since I'm using an inverter for the Schmitt trigger, I'll want to swap the capacitor and resistor. I want the capacitor connected to VCC instead of ground, and I'll connect the resistor to ground instead of VCC. Let's try that out. I'm going to use the upper left inverter on the 74HCT14. So I'll just pull out this termination wire from its input. And I'll just place this pesky little 100k ohm resistor from the input pin to ground. Then I'll add a 0.1 microfarad capacitor from the input pin to the power pin. I'll remove the termination wire on the clear input to the flip-flop, and connect the output of the inverter to that. Excellent. Let's give this a try. And now, no matter how many times I try to power this thing on, the LED starts up unlit. And the switch still toggles the output. Now I'll cycle the power while in the lit state, and it still powers up unlit. Beautiful! Well, this test of the single-step switch wouldn't be complete if we didn't connect it up to the Plague Mark I CPU. So let's pull that project in and connect the power up. And of course, connect the clock output of our new clock source up to the CPU's clock input. Here it goes. And notice that the bar graph LEDs do indeed change each time the clock LED turns off, which is every other switch press. This is all working as expected so far. Well, this video is starting to get pretty long, so I'm going to continue it in the next video. So, what did I accomplish in this video? Well, I came up with a game plan of what I want for this clock source. I want a 2-switch design with a run-stop switch and a single-step switch, and I developed the circuit to debounce these switches. I also implemented the single-step switch. In the next video, I'll work on implementing the functionality of the run-stop switch, and look at some run clock options. That's it for today. Thanks for watching, and I hope you'll join me next time, right here on Dr. Plague.